Okay, so the good news is that I have 150 slides to go through today. So I figure if I do them in 20-second bursts, that will work out really well. What I'm going to try and do today is cover a summary of the course. It includes chapters 1 and 2, which I didn't cover, but I believe I have what was covered in there. I've added some very simple examples for this. If I do make it through this particular presentation, which is about 45 pages, I'm not holding my breath, I do have one on 2021, the final exam, and I will probably cover either that or 2022 tonight in the 5 o'clock lecture. The idea here is really sort of a very, very quick overview of everything that you've covered, everything that we do expect you to know. And it is possible that I have missed some stuff. It's a lot of material, as you can appreciate having. It's a little bit harder to appreciate until you actually hold the book. It's about 600, 700 pages we have covered this term. So, chapter 1, we defined what a fluid is. And when we did that, fluid cannot resist shear stress unlike a solid. Any shear causes continuous deformation, and that's flow. Liquids are treated as nearly incompressible, have a free surface. Gases are compressible, but no free surface. They tend to just sort of rise to fill the room. Hydrostatic forces, no shear anywhere, or hydrostatic, no shear. Pressure is a scalar, and it's the same in all directions. And you've done a number of those gate problems where you looked at what was going to happen when you submerged a gate and looked at the vertical forces and the horizontal forces. Treat properties as smooth fields if the elemental volume is much, much greater than the molecular scale. And so you've also looked at this issue. You can sort of think about it. You know, you have air. You kind of know that there are a whole bunch of molecules with gaps in them. But we have treated air and water as a single sort of continuum. Density is a point function where rho is equal to dm dv, where dv is the smallest volume for which the continuum assumption holds. We haven't really sort of done very much with it. For you in this class, we're going to assume forever that it's just a really small volume and that we don't have to worry about molecular scales. Continuum may fail, or does fail, in rarefied gases, where the mean free path is comparable to the geometry. But again, you haven't really looked at that, and you haven't been focused on that sort of problem. So as far as you're concerned, any fluid you're dealing with, it's probably going to be air or water, is going to be continuum. Primary dimensions are MLT and also theta, theta being temperature. Work in SI or British gravitational units, slug feet second, to avoid hidden constants. Dimensional homogeneity, every additive term carries the same dimension. And one of the things that is really kind of useful, no matter what you're facing in an exam, is to write down the units of what you're calculating. It often helps you sort of figure out how to go about the problem. And you can see that when you look at problems related to dimensional analysis. So if you take a look, for example, at Bernoulli, I can write it in a whole bunch of different ways, but each of those ways has to have consistent dimensions. And you can do that, and you should check it. So if you have a problem on an exam, a really quick way of checking things and saying, hey, do I have the right equation, is to write down your units. We didn't talk very much about thermo. Do you take thermo this term or next term? Oh, last year. Okay. Oh, last year. Okay, so it's all stuff you knew. So you had internal energy, enthalpy, all of the coefficients of pressure and volume. All of those are stuff that are useful to know. We haven't done very much. Perfect gas law is always useful, and P equals rho RT. Newtonian shear stress, you have seen this, and we have applied it pretty much across the entire course, except when there has been static terms. We have defined kinematic viscosity. And finally, to a large extent, I have been jumping to this form of the Reynolds number, but these two are equivalent statements. And again, if you spend the time to look at these things, you'll see that you can confirm all of that for yourself. So, for example, you have a case, and that's not a that jumble at the top is me playing with graphics on LaTeX. I need to fix that later. But SAE 30 at 20 degrees C with a viscosity of 0.29 kilos per meter second between plates, gap of 2 centimeters, top plate moving at 3 meters per second. So you can just calculate. You have tau equals U delta V delta H. The delta V here is 3 meters per second, and the H is 0.02, and you end up with 44 pascals. So again, as you're going through this, I don't always do it, and that's probably not a good idea, but you really should write down the terms that you have. You have gradients of pressure which go as rho g. Delta P, delta Z is minus gamma. I haven't used gamma very much. Perhaps Professor Gunther did, but that's just rho g. And if you have the same fluid at the same horizontal level, they always have the same pressure. And that's how you do all of the manometer per questions and things like that. In compressible liquids, P2 minus P1, excuse me, thank you. P2 minus P1 minus gamma, Z2 minus Z1. And for lakes, you always had atmospheric pressure. And we tend to not use atmospheric pressure at all. We use zero. We use zero gauge. There are very few circumstances where you would have an absolute pressure. But you have to be aware of that. For isothermal cases, you can calculate pressure in terms of the change in height, which is related to the density over RT, and you can do that for atmosphere or standard troposphere. I don't know if, did you ever do that? Did you see these equations? Okay, you should know what they are, but not much more than that. But in terms of manometry, if it moves up, pressure decreases, moves down, pressure increases by rho g delta Z. That's the height difference. You have a pressure on A, a pressure on B. You have two columns of fluid, and you sort of calculate everything across there. The jump across to equal elevations in a continuous fluid is always going to hold true. Differential U-tube with a process fluid, rho 1, and a manometer fluid, rho 2, it's just PA minus PB, which is over there, is rho 2 minus rho 1 GH. And you did, again, you've done a lot of cases where you've looked at manometers of different sorts, often, you know, the red fluid and things like that. Forces on a plane surface is pressure at the center of gravity times its area. Center pressure form is YCP and XCP, and you have moments of inertia that you calculate for both and calculate over the heights. And again, it's really good practice to go through and sort of look at all of these cases. Curved surfaces, you have force on vertical projection. Vertical forces, you have the weight that acts downward on the surface. Archimedes buoyancy, force of buoyancy equals rho g, which is the displacement. And for things that are floating, force of buoyancy equals the weight. Line of action through the center of buoyancy, small angle stability, metacentric height, mg, and you want the height to be greater than 0. Pressure max in the case where you have a freshwater lake with a depth of 60 meters and the absolute pressure or the atmospheric pressure around it is 91 kPa. You can say it's 91,000 plus density of water times 60 meters, and you end up with 678 kilopascals. Where I came into the course, you had already started to do control volumes. And control volumes have always been a really important part of the course because we want to sort of have you look at conservation of mass, momentum, angular momentum. And you'll see that when I start to talk a little bit about a past exam. So I'll probably focus in at this point on 2021. In the aid sheet, and I am likely to change it a little bit. I'm still working on it, so I haven't quite figured out what I want to do. I have updated a version to include Swami Jain, but you already have all of this. Go ahead.
Will we get a double aid sheet again, like on the midterms?
Yeah, I think so. I don't think we're going to change that. I might change that next year. I do find it's kind of ridiculous to have 2 aid sheets. Yeah. Yeah? Oh, sorry, yeah, I should have mentioned all of these. The reasons I didn't post any of the slides for this week is I'm just going to post one set of slides on Tuesday at 5:30. It's already done, but I don't really, I want you to attend. And it's always helpful to get you to attend in these cases. You can do whatever you want to. I'm not here to stop you from taking pictures. But you will get the complete version. So everything that you see here is going to be posted. Mass in equals mass out. And that's been sort of the fundamental equation that you've dealt with in the course. And it's rho AV. And so you've seen it in a number of different cases. On the last midterm, you had the case where you had the nozzle with things sort of rotating around. You also had to think a little bit about that when you looked at the momentum equation because it depended on direction. Bernoulli equation, that was also on the last exam. Frictionless terms, P over rho g. And we generally write it in head form just because it's easier to deal with. That doesn't mean anything. You can write it any form you want to. You can multiply across by rho g. You can do whatever. But as long as you sort of hold to some consistent measurement. So don't write rho gz plus p over rho g. Just make sure you have the correct form of it. Use gauge pressures for free jets. You always have gauge pressures because you're always dealing with atmospheric pressure in those cases. Include pressure on CV faces, choose axes, and sign carefully. And you know, number one thing with all of that is draw the picture. You know, as long as you draw the picture or even draw it directly on the problem that you have, that will help you solve things. Nozzle reactions, pick a CV around the nozzle, outlets to atmosphere is 0 gauge, continuity for unknown inlet velocities usually. Apply momentum in X and Y to get both forces. This was probably directly related to, well, okay. R for vertical jet is m dot v1 for momentum. R equals weight because you have a plate that's being suspended. And so the plate is being held by by weight, or is opposing the weight, or the jet is opposing the weight. Bernoulli from nozzle exit to plate for height h. I think this is really the most important chapter that you have. Everything else you do in chapters 6 and 7 really comes down to this idea that you can take a whole bunch of different results and come up with dimensionless groups that make sense. And if you look at what the workhorse for mechanical engineering fluids is, it's Reynolds number. And Reynolds numbers has been crucial for all of the terms that we're looking at and how we track things. So it collapses many variables into single or a few dimensionless groups, turn 10,000 experiments into 10 by plotting a constant for a various pi group. You're familiar with Buckingham pi. On the midterm, you proved it. It was a problem that you all did very well on. If n variables, m base dimensions, k equals n minus m dimensionless group. You have always had a list of potential dimensionless groups that would be helpful, and they should somehow guide you as you think about things. So, for example, Froude number when you're dealing with free surfaces, Weber number when you're dealing with surface tension, Mach number, Euler number is for pressure. Euler number is for pressure, but it's for pressure. It becomes sort of various C sub p's that we look at. Strouhal number for vortex shedding, and Mach number for compressibility effects. So you can do this if you want to match all of your relevant pi groups. So, and we talked a lot about this issue where ideally I would live in a world where I could afford to run the same experiment at the same Froude number, same Reynolds number, and everything else. In addition to all of the Wemyss issues that would probably arise from that, the costs would be completely crazy. On the other hand, you can make choices where you say, hey, I think it's more important to match Froude number than it is to match Reynolds number. Or, for example, if I look at the various lift over drag coefficients that we had, there's a certain point where you reach a constant lift factor no matter what your Reynolds number are. So you can drop down your Reynolds number and increase your Froude number to match what you want. Always write units. It really is crucial. One of the easiest mistakes to make in an exam is not to write the units down, and then you sort of miss things. Choose m repeating variables. Often we will tell you what that is on an exam. In life, you're going to choose your own. In life, you will be determining that partially by guidance from other existing dimensionless groups. In fact, I doubt very much that I have used Buckingham Pi's theorem other than to sort of confirm something in a class. Mostly, I will look at what other people have documented. Build each pi group with a non-repeater and solve exponents so pi is dimensionless. And state the final relationship. And try to identify the known groups. From there we went and we spent a bit of time on viscous flow and ducts because that really is kind of the important section. We've defined in the course 2300 as transition for pipes and an entrance length that is 0.06 Reynolds number based on diameter for laminar flow, and 1.6 Reynolds number to the 1/4 based on, again, Reynolds number based on diameter for turbulent flow. Those are the sorts of things you keep in the back of your head as you solve things. Unlike previous years, with the TAs and the tutorials, have they been using Moody diagram or any other type of approach? Moody. Okay, so you're free to use whatever you want to. We do expect you to know how to do Moody diagram and show things on a Moody diagram. But you're allowed to solve it with this. Go ahead.
Would you ever ask us to explicitly solve with a Howland or Swami-Jain? Or are we always, like to iterate, we would have to use Howland, right? Is that
Oh, no, you can use, okay, so I ran into Holland equation in July when I started rewriting these notes. And so I used Holland because I knew about Holland and I've used it for years. I ran into Swami-Jain in the middle of this term. And I really like Swami Jain because one of the reasons is that you can see that Holland is a square root of f. F is a direct term. If you were asked for something, let's say we would ask you for something about Moody diagram and to iterate on the Moody diagram. You are allowed to say, I have iterated on Swami Jain. Here's the line that I got on the Moody diagram. And honestly, I would do it that way. And of the two equations, again, they're both not that difficult. But I actually find Swami Jain may be better. There are two other relationships, and I talked about in the lectures associated with that, which would have been about 5, 6 lectures ago, so 30, 31, somewhere around there, about the problems with Swami Jain for Q and D calculations. But Q and D calculations are also there. But I would avoid those for now, unless you're absolutely certain that you have the correct physics for the Swami Jain in those explicit relationships. The other thing that you have looked at are minor losses. And you have had a number of different cases where you've gotten K factors for sharp entrances, valves, various other terms. You've pulled them off of charts. You've done all sorts of things. All of those are expected that you would know them, plus you have what we term the major losses. So again, minor losses are not minor in the sense that they are a low percentage of the total loss. Often they are a significant percentage, or it could be a great percentage. You have looked at 4 types of problems, or 3 types of problems. Head loss, you're given d, L, Q, rho, mu, E, epsilon. Compute velocity, Reynolds number, F. And there I'm kind of switching a little bit to Swami Jain. Again, even in a type 1 problem, which does not require any iteration, I still would use Holland equation or Swami Jain. I would then draw on the Moody diagram. Here's how I got that number. Thank you very much. So that you say, I've confirmed that this is correct. But you are absolutely allowed to do it whatever way you want to. But we do need the answer to the form we asked for. There you go. Flow rate. You know, say a head loss, iterate between V and F. Type 3 sizing, Q and delta P, iterate D to F. If F is assumed, you have an equation for D, which you can then use. So you just keep iterating until you get the right answer. D changes. As D changes, Q changes, Reynolds number changes, and then you can either, you again have the option of going to the Moody diagram, Holland, or Swami Jain. And before the exam, I strongly urge you, before the exam, try a couple of type 2, type 3 problems, and I've already given you pretty detailed problems in the last set of lectures for chapter 6. Do those on your own, confirm that you're able to do them, and get the right answer, and choose which way you like best. Once you decide, it's straightforward. The only other thing is hydraulic diameter. We talked a little bit about it. We didn't do very much with it. I did a couple examples on that, looking at, I think, a square duct and a annulus. We finished the course with external flow. So last Friday we covered all of that. We talk a little bit about how we define delta, the boundary layer thickness, and that really should be sort of shifted over here somewhere. So a delta laminar versus a delta turbulent. And the growth rate of one versus the other for a constant flat plate, or a flow rate over a constant flow rate over a flat plate for laminar Blasius solutions, 5 over square root Reynolds number x, coefficient of friction 0.664 over Reynolds number x. For turbulent flow, again, remember, Blasius is an exact solution. That's one that you have. You can go through all of the effort to solve it. Turbulence, you're going to have to play a few games. So it's useful to sort of recognize that, but in the end, you really need to know what the relationships are and recognize them. Plate drag, laminar over length, CD is equal to 1.328 over square root of Reynolds number. Transitional turbulent numbers adjust, and we've talked about that. And I have updated the aid sheet to include that. I do remember I did that, so I will try and do that by the end of the week. I'm not expecting a lot of urgency on your part until next Wednesday. When's your last exam before fluids? 17th. Yeah, all right. So 18th, 17th, 18th, I'm expecting that I'll have everything certainly done. Adverse pressure gradient, del P, del X greater than 0, S-shaped profile, you have reversing flow. We took a look at a lot of different cases, separation and big pressure drag. Favorable pressure gradient, del P, del X is less than 0, thinner, stable boundary layer, separation does not occur. So the first one, just very straightforward. Find the head loss. You're given everything else. You calculate the area. You calculate the Reynolds number. And once you do that, oh, that's interesting. You have Swami-Jain. You can calculate the terms. And Darcy-Weisbach to calculate the head loss. These are not worked examples. These are examples that you are free to do on your own to sort of make sure that sheet is probably not valid anymore. No. I do have, I'm looking at the sheet making sure that I have everything that I needed. It had everything for quiz 2, which was enough for me. But next year they'll have a full aid sheet, and I won't have to do any more afterwards. Guess velocity, compute Reynolds number and F. Again, I'm putting Swami-Jain. I just think that looking at the two forms of the equation, I'm less likely to make a calculator error with Swami-Jain than I am with Holland. Holland, I need to remember I have 1 over square root of F, and for Swami-Jain, I just have F. And so the fact that I can write it that way and write it very quickly means that my solution gets a lot easier. And you can, again, if the tutorials have all been using Moody diagram, all of those questions are valid for you to go back over and try on your own to confirm that you can solve them using Holland or Swami-Jain. And again, confirm which one you like better. Update V from Darcy-Weisbach to meet H of F. Iterate, keep iterating. You'll get Q equals 0.05, and 2 to 3 iterations actually satisfy this. Finally, or not finally, you got reservoir discharge with an elevation drop, given a whole bunch of terms. You have the energy equation. You start with a guess. You calculate F from Swami-Jain, update it until it's converged, and the result for this particular configuration is going to be 2.1 cubic meters per second. Ignoring, so this is where the risk is. If you go back over the notes, and I haven't included this, and I'm not going to include this on the aid sheet because I think it would be a red herring and too many people would fall into it, where they would write Q and say, hey, there's an equation for Q in there, but forget about anything else. And so if there's anything, you can see what exactly would happen in those cases. Diameter sizing given Q and HF. You guess D, you get an area, get Reynolds number. Again, the amount of work doing a Swami-Jain or a Holland equation is not that much. And then if you're required to use the Moody diagram as your solution, which again may happen, you can just draw it in. Update D until they match. And now in this particular case, you can use, so this is the diameter expression. There's no minor losses in this particular case. They will match, the result will match with Swami-Jain, and that's the Swami-Jain relationship for that particular case. Nothing is guaranteed, but we are not very clever people. We don't spend a lot of time redoing exams and rethinking what we want to cover. So I strongly encourage you to look back at previous exams. Go ahead.
Some of the parts from the first course might come into the final, right? Or
Oh, absolutely. Absolutely.
And is Gunther exclusively writing from the first half?
Yes.
You guys-
Yeah. So CV momentum with forces, energy Bernoulli equation with head losses, pump power, pipe flow iterations, pi theorem, derivations, external flow or flow estimates. Ultimately, in all of these cases, you go back to first principles. You have control volumes, you have continuity, you have momentum. You always start with a guess for velocity or diameter, and it is better to iterate on F than it is to use the explicit relationships for any of the other cases. If you use the iteration on F, you're less likely to run into a physics problem where Swami-Jain does not apply. Use energy equation to update unknowns, repeat until the change is less than 1%, and you have the 4-step recipe slide, which is already there. So in terms of quick formula sheet, I'm just putting down the ones I remember and I think are useful. Again, the 8 sheet will be updated. I just need time. So you've got mass flow, momentum, and those are the steady state cases. Bernoulli there. On the right-hand side, you have all of the relationships that we have for friction. So Colebrook-White, which is the implicit relationship, and Holland and Swami-Jain. And again, this is a great chance for you to sort of say, hey, let me try both ways, just to get a sense of which one's better for me. Darcy-Weisbach, laminar flow, hydraulic diameter. Okay, this one, okay, this is not a complete sheet. And again, I keep sort of looking at things and rewriting them. You have minor losses, you have Reynolds number, Froude number, Weber number, Euler number, Mach number, Struhal number, you've seen all of those. The relationships for flat plate laminar and turbulent flows, we look a lot at flat plates and plate drag, but there's not much there. So I haven't included in that chapter 1 and 2. It is included on the aid sheet. Any questions on this? Usually, yeah. Yeah, because I can't think of a really good way to ask a question and get what I want out of you in terms of results. It can be a mess if I don't give that kind of guidance. Okay. And we have to sort of look at it from that perspective. What do we want? Okay. So again, on Tuesday around 5:30, I will release all of the final exams that I have. I have managed to solve through. These are my own solutions. If you find an error, tell me, just so I know and I can correct them. And if you find them before Wednesday next week, I'd really appreciate it. So final exam. And you have a shower head, has 200 nozzles, inner diameter of 2 millimeters. Total flow is 9 liters per minute. Is flow in each nozzle laminar or turbulent? So again, I think I took the wording exactly out of this, but you are going to assume that the flow distribution is equal. So in each of the nozzles, it's getting the same amount of water as any other nozzle. So when you divide it, you get 0.045 liters per minute. And then you divide it out, solve for cubic meters per second, and you end up with 7.5 times 10 to the minus 7th meters cubed per second per nozzle. The area per nozzle, you then calculate 0.002 squared over 4. You end up with 3.14 times 10 to the minus 6 meters squared. Velocity is just going to be Q over area, and you get a Reynolds number of 478. And that's going to be lower than what we've defined as turbulent. Very much lower. You're still required to know British gravitational units. That still is part of this course. But again, you can, if you have a chance, convert to SI units and solve things. If you're doing these questions on your own at home and practicing, practice switching back and forth. It's often easier. Again, I have a lot of difficulty doing G, G sub C, pound force, pound mass, and all of the conversions. Laminar oil in 5 sections, A to E. And if you notice, these 20-foot sections have these various manometers that have been placed in there, 60 inches, 20-foot sections, 5 feet from the flange, 56 inches to the next one, 46 inches, 10 feet to the flange, or to the manometer or psilometer, etc., 15 feet, 6 inches. So with a problem like this, make sure you know where you are, because you have a thing that's going 0 to 20 to 40, and so the third piezometer is 50 feet downstream. You should know all of that as you're looking at these problems. You have Hagen-Poiseuille, and you can calculate all of the terms. Did I forget the diameters? Oh yeah, so the other thing, and I don't have it on the problem, is I think the diameter's changed. Oh, no, you were supposed to identify the smallest diameter. Okay, sorry. I just have to remember the problem. So you had to identify the smallest diameter section, and the largest delta P associated with the travel distance is going to be the smallest diameter. And so you can calculate for Hagen-Poiseuille 128 mu LQ pi d4. Delta P from unit or distance to distance gives you pressure drop per unit length. And from there, you calculate what your section lengths are. And if you solve through for all of this, you can do you can calculate that section D has the largest slope and is the one that will solve. So, oh wait, maybe not. So just remember, you have this relationship that's constant for every term except for pressure, or sorry, diameter. So over here, this is constant, this is constant, this is constant. No, not this. This is constant, and Q is constant. So you don't have to look at everything. You just have to say, okay, there's going to be a relationship for D, and use that to calculate what your term is. Oh. We've done a lot looking at drag on plates. Laminar boundary layer on flat plate. What fraction of total drag occurs in the first 10% of length? Skin friction is going to go as x to the minus 1/2. You calculate shear at the wall as a function of x to the minus 1/2. Do the integral, and that's not a bad integral. You end up with 2 as a function of L. So for the first percentage, and it's laminar. So for the first percentage, you get square root of 0.1 L over L is going to be square root of 0.1, or 31.6% of drag in the first 10. Those of you who haven't figured it out yet, I'm using LaTeX, and occasionally I forget where exactly my math equations are, and I end up with math equation format at the bottom, jumbling all my numbers together. The front of the plate has the thinnest boundary layer and highest shear at the wall. And that kind of makes sense. You have a shear that's going from 0 to the very top, and then as this grows, that shear gradient, del U, del Y, is getting smaller. And so it makes sense that a very large percentage would be in the first 10%. That's a gopher. 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 You're asked if it's a biology course too, surprise. You're expected to know and identify genus and species. That's part of the exam points. So velocity 1 is 6 meters per second. Velocity 2 is 1.07 v1. Estimate p1 minus p2. So you have v naught, which is going over, and then you have a small ramp. So the groundhog typically builds a small mound and sticks its head out and goes to take a look around. It's a Bernoulli question. And you know it's a Bernoulli question because you have the change in area, you have no change in pressure, and you have no change in height, really. So this is a problem where you could argue you might have a small change in height, but again, the error associated with that, the heights are going to be very small compared to the change in inertia. So P1 minus P2 is going to be the difference between V2 squared minus V1 squared, which you are given. V2 you can calculate and do all the numbers, and you end up with 3.13 pascals. Oh, maybe just. Again, one of the things that you really have to recognize is that Bernoulli equation, speed up, pressure down. The mound accelerates air because it sort of brings the cross-sectional area down a small percentage. So as it goes around, it's driving the ventilation in the shaft, which is why the groundhog is happy to be in the tunnel. This is a kind of interesting problem. Wood block with rho-g specific weight of 45 pounds per cubic foot, floats in oil, 56.35 pounds per cubic foot, over water of 62.4 pounds force per cubic foot. Oil layer is 0.5 feet, cube is 1 cubic foot. Find the H above the oil. So you're given, you know what the weight of the block is because you're given its specific gravity. You know what the oil is, you know what the water is, and you know the distance for the water, or sorry, for the oil. You don't know the distance for the water. So straightforward because it's 1 cubic foot, so it's 45 pound force. The volume of oil is 0.5 cubic feet. And you have, for force on the oil, you have 28.175. And the water has a buoyancy force which is 62.4 times the height of the water. 45, you put all the numbers together, you know you have to have it float. And you get the height of water, which is 0.27 feet, and which leaves about 0.23 feet at the end. So these are, oh no, these are the standard questions. So this is second question on the exam. I'm just trying to see what my time is. I have about 100 slides left. So total buoyancy is the sum from each fluid, so I calculate that, and that's all you're going to do with these types of problems. Dimensionless analysis, make sure you know how to do it. You have some sort of force. You're given all of the terms. Just sort of statements on this. I don't remember where I got these equations from. I think I stole them from school. But the question or the problem statements are more detailed than what I'm giving you here. So if you get a chance, you should take a look at them, and I need to update these things. Anyway, so you got to find pi groups, Reynolds number, and Froude number, and what would happen if you add theta. So you have 8 pi groups, 3 sort of important dimensions. You get 5 or 8 or 8 variables, 3 repeating variables, MLT, k equals 5, and you end up getting pi 1, pi 2, pi 3, pi 4, pi 5 for each of those, and you kind of recognize all of them. So this is sort of a Euler number, I guess, Reynolds number, that's a Froude number, Struhal number, and another Euler number. If you add in theta, so you worry about temperature, then you have 9 terms you got to add in, and you have 6 terms, and you end up k equals n minus r, and you solve through. So you can do scaling on that, and I am going to stop with it there, and I just want to go through one sort of thing. So on each of the questions, what I've tried to do is break it down into what's been covered. So yeah, there's in all of this stuff, we do cover chapters 2, chapters 3, chapter 6, chapter 7, chapter 5. We're not covering chapter 4. I did cover chapter 4. I think I gave it one lecture on that. I think it's an important chapter, but we don't tend to cover it. So chapters 1 and 2 are sort of implied in this. Units, shear, all of that stuff is stuff that you've carried through all the way through. And what I've done with each of the exams is the same sort of thing. So, okay, here's how we've kind of looked at these problems. You'll notice chapter 7 is covered as well. You really, I mean, the goal is really to identify what we're asking. Is it energy, momentum, mass problem? I mean, to a very simple sort of, a great simplification, we are asking for energy, mass, and momentum every time, even with the chapter 6 and chapter 7 questions. Bernoulli, modified Bernoulli, the full equation. When is the flow laminar? Knowing the conditions and limitations of each formula is crucial, particularly with chapter 7. So when I dealt with chapter 7, we don't have any of the sort of equations. So I have Holland and I have Swamitjane, which makes my life a lot easier in chapter 6. Chapter 7, I don't have that. There's one equation I think I gave you at one point, and I forget what it was. But beyond that, nothing else. So chapter 7, you need to recognize the limits and when exactly a flow is laminar, when it's turbulent. And I have, again, I've updated the aid sheet. I haven't posted it for that. Your most important friend in all exams is to write your units down. I can't stress that enough, recognizing what they are and how to do the conversions. Always sketch a control volume. You're always safe doing that. Write down knowns and unknowns, and a clear setup is the fastest way to a correct answer. Okay, control volume laws, chapter 3, internal flows, chapter 6, yep. Internal flows, chapter 6, hydrostatics, chapter 2. Chapter 1 doesn't have very much in it, okay? It's really, here is unit and a fluid is this. But ultimately, you use that all the way through it. You need to know that a fluid just displaces. External flows, dimensional analysis, and that's the end of it. So I still have another 60 slides. I do. There you go. Yeah, 64. All right, I will not have office hours this week because I know it's kind of pointless, but I will have office hours next week. I'll try and decide when the best time is. I recognize some of you have a bio exam, and I'll work around that. Thank you very much, and I will see you on the 19th.